my primary work has actually been in the design of circuit boards, like I guess most of you guys here. So this is based a lot on my experience, and I compiled this into a book many years ago. And so it's called EMC at the component and PCB level. So if you are interested in getting more details on this, obviously I would recommend going buy my book. It's on Amazon. So why am I looking at component selection? Well, it can have quite an impact on your EMC performance of your design. Perhaps not as much as the circuit board to some extent, but you can do things with the components which we'll have a look through these types of components and see what we can do. But it can also reduce the cost, because some of the things I'm going to suggest are not necessarily going for better or more sophisticated components. It's actually to, well, as you'll see as we go through, perhaps use a more consistent type of component which can reduce your cost because you go up in volumes. Now, I've got 45 slides, so I'm going quite quickly because there's a lot to get through. This is an abridged version of a whole day event I do on PCB at the EMC at the component PCB level. In general, whenever we go through this, component packaging is going to be one of the things that has quite a big impact on your EMC performance or what you can get out of your product. We heard downstairs about the fact that sometimes the ground connection isn't just a ground connection. It might be actually a sense ground, and so you don't want to put current through it, etc. I presume you all heard that question in Lee Rich's talk, and of course it's not marked up on the data sheet, so you don't necessarily know that. So there are issues with packaging which might actually be very difficult for you to get a handle on exactly what's happening, but it will impact the EMC performance of your circuit. In general, I tend to state that surface mount is better. This isn't true for inductors, which are wire wound, but in general, surface mount is better. And it's not necessarily because they always have the lowest parasitics, but they have the most consistent. So if you've done something to help your EMC performance, you know when you go from one 0805 capacitor to the next, you're going to get roughly exactly the same performance, whereas with leaded parts, that's not true. Does anybody here still use leaded parts? I still do a lot of mains and high power design, and there's certain products which you can not get in surface mount. So there is still quite a lot of leaded parts around. In general, smaller parts are better, so if you can go to a slightly smaller package, 0603 instead of 0805 or 0402, as long as it gives you the functional performance, and at the end of the day, the EMC performance will always be secondary to that, that can give you a slightly better performance. Again, for the same reason, you get lower parasitics. And in particular, you need to be aware of these mechanical, these effects, these parasitics are generally mechanical effects of the package. It's made up of bits of metal, and that mechanics is what defines the parasitics you're going to get. Now, you can control some of the parasitics in your PCB layout, but the parasitics of the package are given to you, and you can't do much about them except be aware of them, and therefore select a component which gives you the best performance for your circuit board. And in particular, one thing I've come across which has significant impact on the EMC performance is sockets. Sockets are really useful when you're developing a board to test out an IC and maybe chop and change, particularly if you've got one-time programmable devices, although these days that's not always such a common thing. And so it's quite convenient, but they add a massive amount of parasitics to your performance. And doing any testing EMC-wise on a socketed product compared to a mounted product will give you very, very different performance. And typically, you might, in fact, have to over-engineer some of the decoupling capacitance on a socket compared to what you need to do with a placed component. So often, if you design in and try and test with a socket, you're going to be adding expense to your final circuit board, which won't necessarily be there when you remove the socket and go for a placed part. So I always suggest it's actually cheaper in the long run to not have socketed parts. Just have more boards. More boards can be cheaper than sockets sometimes as well. So I'm going to go through those different types of component, but in general, the passives are the easier one to get your benefits from. And that's more because often the active parts are more defined these days, as we've been hearing, by the software people, because the performance of the higher end parts are determined more by the software requirements than they are by the hardware requirements these days, in my experience. And so it's often easier to change the passives, and to some extent, some of the passives can have as big an impact, if not a bigger impact, on the actual EMC performance. So where you can use surface mount, again, this is going to be a common theme. In particular with surface mount resistors, the carbon and the soft film types actually have higher losses. Now that, if you're doing high-speed design, that, and if you listened to Lee earlier, that's not what you want necessarily. But the thing is, for EMC, you want to get rid of those high speeds in general for your resistor. Your resistor's in there for usually a DC or at least a lowish frequency. And so having things which are high loss mean that a simple resistor can actually give you quite good high-frequency rejection for no extra cost, but only if you use the lossy materials, carbon film and the softer films, but not metal. Metal films actually are very good inductors at high frequencies, so they're not necessarily the best technology to use. I'm not going to go into the wire wound, but again, there are things you can do with winding style, but as there's only me and that guy over there who use through-hole comparts, I think we'll give that a miss. Now, when I started doing this quite a while ago, a lot of the resistor companies used to say, oh, we've got this special low noise resistor, which are great for audio circuits. Yeah, they are great for us. They make no difference on EMC and they cost a bit more. So if any of your resistor suppliers come to you and say, oh yeah, this is better for you for EMC because it's a low noise, no, it's not. It doesn't matter. Noise voltage on a resistor does not impact EMC in general. So no point buying them. One of the curious effects you have with surface mount, there we go, surface mount resistors is that they have a flat line, what I call a flat line. There's a value per size where they're virtually resistive across the whole frequency spectrum. As I say, they're not resistors all the way. So if you have a higher value, obviously it's got more windings, if you like. It's obviously not there as a winding, it's there as a resistive element. It becomes an inductor at high frequencies. If you have a small value, not much winding, the end caps on the resistor at high frequencies become capacitors. So those caps literally become capacitors. And so depending on the value and the size, so typically at 08, 05 it's 100 ohms, it's 47-ish ohms, it's actually a little less than that, 06, 03, and about 33 at 04, 02. So if you know that, you can actually gain some benefit to your design by the use of a simple resistor. So if you want to, for example, reject high frequencies, use higher value resistors. Now, if you want 100 ohms, that might not be that convenient, but often resistors are so cheap, it might be better for you to have two 220s, which are going to give you a high frequency rejection than a single 100 ohms, given how low cost they are and how simple they are to place. Likewise, if you actually want to get signals through at high frequencies, maybe you're better with two 47 ohms in series, because they'll let the high frequencies through. So you can do this without having to spend any more money on a special part that explicitly gets you through this, just the choice of the component value and its physical dimensions. And if anyone's interested in getting, I have a little table of some of the sizes and what their flatline value is. And so if you, my email is on the back of this, unlike Lee's, unfortunately. So at the end of this, if you want to get in touch with me, I can send you that table. It's no problem. With capacitors, again, surface mount, but it's not really for the parasitics. It's more for the fact that, again, you've got a controlled effect. Although this does limit the actual frequency response you'll get out of a component. There are actually, on the data sheet for capacitors, parameters which tell you to some extent how good its EMC performance will be. It's not there for its EMC performance, but it does help. And one of them is the equivalent series resistance and equivalent series inductance. And are you familiar with these terms? Is everyone familiar with these terms? Good. And you can actually use these terms and a simple model to calculate these in a SPICE or other type of analog circuit simulator if you want, to get a much better estimate of what impact capacitors are going to have on your circuit. The worst one actually is this one, equivalent series inductance, and this is the impact that surface mount most has on the performance, the ultimate EMC performance of ceramic capacitors. Now, ceramic capacitors have other issues. You might think I'm paying more for MPO than Y5V, it should be a better frequency performance. Actually, at frequency terms, it makes virtually no difference whatsoever. So, be aware that for EMC performance, just on frequency performance, the higher cost, I won't say better, the higher cost ceramics don't necessarily give you a better performance, but they might do. And often capacitors, particularly surface mount ones, are a very good cure for a lot of EMC problems at the circuit board level. So component suppliers are actually incredibly generous, because you go and buy this capacitor and they throw in for free all these other components. So they're extremely generous to you. Some of these you can get from the data sheet. You can't get this value often, which is the dissipating resistance of the capacitor. And I include that here because if you are trying to do a simulation, you have to put something in there because otherwise the model might not settle. So you can put in a 10 meg ohm resistor there if you don't have the value. But typically that has to be in the model in a simulation, otherwise the model itself might not solve. So that's the main reason for involving it. But this is the equivalent series inductance, which actually is an effect of the electrodes in a surface mount capacitor. For those who, the ceramic multi-layers are made up of a series of interdigitated metal plates between ceramic material. In the case of tantalum, it's a rod inserted into a metal can. And with electrolytics, it's two foils wound around each other. So you can imagine they have quite different but significant impacts on the performance of the capacitors. And the main impact they have is on this value here, the equivalent series inductance. Equivalent series resistance is actually less affected by that. It's more, it should be material dominated, but you'll find that often it's the construction that actually limits the performance of a capacitor in this respect. And that's because we're looking at it in frequency terms. So we're not really interested in the resistance, we're interested in the impedance. And people, in my experience, often get confused because we talk about it in ohms. They think of it as resistance and forget that it's actually got a frequency-dependent effect on it. And just to give you, this is a chart of roughly where these are used, not necessarily where they're applicable, but where they're used. And the main reason why, for example, aluminium electrolytics don't go above, or typically don't do much for you above 10 kilohertz, is due to their construction. It's got nothing to do with the electrolyte itself. It can actually operate quite happily in small samples up to megahertz regions. But because of the construction of these large foils coiled around each other, it limits the actual frequency performance you will get out of it. Likewise, most of the others, including the tantalum. And in fact, tantalum, even though this suggests you could use them up to megahertz range, the construction really limits how good they are in that range. For me personally, I tend to stick to just two types, aluminium electrolytic and ceramic surface mounts. And again, that helps because that means you've got a series of constructions on your board which are in roughly 2 frequency bands, which mean that you can very easily, if you have to, filter out certain frequencies because you know you've only got a very limited content in your circuit board. And again, because that's pumping in volumes to just 2 areas of purchasing, it can reduce your overall costs. Plus these days, tantalum's a rare earth metal and quite limited, and we shouldn't perhaps be using it for other reasons, but that's not the reason I stopped using it. It was purely because of its performance. Yeah, of course you can. The newer ones that we have now are polymers. They should sit actually very similar to this polystyrene one. But it will depend on the construction again. Now, I use some polymers for high voltages, and of course they're lucky if you can get up here because of their construction. But in a surface mount form, they should stick down here with the polystyrene ones. Yeah. Yeah, you're not talking about the organic semiconductor ones, are you? Polymer ones, yeah. Yeah. Well, organic semiconductors fit actually into here, but they can actually extend, in theory, the range down. But actually, the construction still limits it. So although they do have a better lower series resistance, because of this series inductance, you don't always at high frequencies get the performance. At DC, you get a really good improvement in performance in hold-up capacitance. But at the high frequencies, it actually makes surprisingly little difference. I'm quite keen on OSCON and the organic semiconductor capacitor technologies. I've used them a lot to great effect, but not for EMC, for DC and hold-up performance. Now, if you look at, as I was saying earlier, if you look at these materials, if you actually look at the data sheets, in theory, the cheaper material, Y5V, actually has slightly higher self-resonant frequency. And that's the resonant frequency of the material itself, not in any construction. So any capacitor, typically any surface mount monolithic ceramic capacitor is not a capacitor above 40 megahertz in general. So after 40 megahertz, you've got plates in air. That's as good as it's going to get. You're not actually using the electrolyte. So all of them are not really very good above 40 megahertz as a capacitor. They're still there. You've still got these plates. It's still something. It's just not necessarily the values you think it's going to be. And although earlier I said about having leads, the thing about leads, this is a ceramic, 10 microfarad ceramic disc capacitor. So I think in a later slide I'm going to show you some ceramic surface mount capacitors in a similar value. The thing about it is, if you imagine you've cut the leads off, the self-resonant frequency is obviously coming around a megahertz. It's not actually making that much difference at a megahertz. It's when you're up here it starts to make a difference. So here at 10 megahertz, you've got nearly 10 times the impedance to ground. So it's not doing 10 times as less rejection at 10 megahertz just because it's got leads on it of 15 millimeters. That's 7.5 millimeters a side, by the way. That's not 15 millimeters a side. That's, even I can cut better than that. And this is a problem with tantalum. Tantalum are actually one of the areas where the equivalent series resistance limits its rejection at frequencies. So typically a capacitor should go virtually down ideally, and then after its self-resonance come up again. But with tantalum, we have ESRs in the ohm range. So that might sound quite good at rejecting frequencies. It's really poor when you compare it to a ceramic capacitor of a similar value, which is down to around 0.1 of an ohm, whereas it's nearly 3 ohms for the equivalent tantalum capacitor. So although tantalums are okay at hold-up voltage again, they're really poor at high-frequency rejection. And it's not, at the higher frequency end, it doesn't make as much difference. It's actually in this middle 100 kilohertz to 1 megahertz, which in my experience is often where your switching frequencies are if you've got a switching power supply. So it's right where you don't need it to be poor, whereas with ceramic chips, you're getting much, much better rejection of these frequencies in the middle range. Now you can see that earlier I said that all these are self-resonant around about 40 megahertz, yet none of them are yet achieving 40 megahertz before they've gone through that self-resonance. This is going back to my original statement. The package has a bigger effect than the natural resonance of the material itself. So these are all 0805, although it doesn't say that, except for this one. This was a test by, I can't remember the name of the company now, I think it was Cypher, who did an 0508, so they changed the format of the package. And sure enough, it widened out the point where the impedance of the leads came on, because it was a different form factor. Instead of being long and thin, it was wide and narrow. But it still didn't have a significant impact. It's not significant enough for people to pay the extra to change the board and go for 0508 instead of 0805. But I include it here just because it does illustrate the fact that it is the package that is the limiting part. And of course, the value of the actual capacitance has an impact. But you see, these are all 0805s, and as you can see on the 0805s, they all tend off in the same direction, even though you might expect, actually, the lower values not to do that because they have less plates in them. But it just so happens that because of that construction, less plates, but at high frequency, the end capacitors and the metal in that become the dominant inductive element in the construction of a capacitor. So typically, even with good ceramic capacitors, you're not getting a lot of rejection above the megahertz region. But you can improve that with using lots of them, because they add in parallel, and that pushes it all down. And that's another good reason to try and use similar value capacitors throughout a circuit board, because as you will see here, if you start using different values, you get different resonant points, and what you will get potentially is interaction between those and resonance between different value capacitors, and that's something else you want to avoid with capacitors. But the reason why perhaps you should pay a bit more for COG, MPO, rather than cheap Y5V, is because they have a voltage bias. Now, this voltage bias is independent of the rating of the capacitor. which came as an absolute surprise and shock to me when I did this. These are test results, by the way. I was fortunate enough to have an impedance analyzer with a voltage bias system, and whether this was a 5-volt Y5V or a 25-volt Y5V, this is how the Y5V capacitance fell off with applied voltage. Which, as I say, actually it shocked me. I was expecting it to move up as the voltage rating moved up. Yes?
What's the nominal voltage in this sheet of capacitors?
I think they were all 50 volt, actually, in this sheet, but I did test a lot of them at 25, and I think I had, it was a lower voltage. I think it was 50, no, it can't have been 15. There was a lower voltage one as well. I was surprised that I didn't get any difference, that the curves were exactly the same. In fact, so I could actually get let's say, a 5-volt capacitor, and it would go on up to 30 volts, actually, without breaking down, but still dropped off like this. I was surprised at two effects: the fact it didn't break down, and the fact that it has just as poor drop-off at 50-volt rated as it did at 5-volt rated.
How does a 6.3 volt capacitor perform at 5 volt? So if I look at the sheet, it must be rather acceptable.
If you're using, yeah, exactly. So, yeah, if you're using a Y5V and you're not going above a few volts, yeah, absolutely. In fact, I have standardized personally on X7R because I very rarely go above 15 volts, and so that's an acceptable drop for me, given the cost difference and the dimensions you can get in value. But that's for you to make, depending on your board, not for me to tell you. That's how I've done it, but that's because I primarily work below 12 volts in most of my circuit. Yeah.
Does package size have any influence on this?
No. I was surprised at that as well. I didn't do many package size differences, but I think I did an 06, 03, 08, 05, and 12, 10, and I couldn't see any difference either. So that's not a big range, but yeah. But this should be in the manufacturer's data, but it's not always there. And then, of course, this is another big difference is temperature. So Y5V, this is why I actually went away. This is the reason why I completely went away from Y5V in the end. It was actually the temperature performance. So again, at, say, 40 degrees Celsius, just so happens that they all peak at room temperature, which is where we all do our testing, of course. So that's a bit of a coincidence, I'm sure. But say just 20 degrees up, you've lost 10%. If you've then got a bias of 10 volts, you've lost another 50%. You've got very, very little left in a Y5V capacitor. Not that I'm here to badmouth Y5V capacitors. You can make your own decision on that. So when we put capacitors in parallel, generally it's quite a good idea, but you have to be conscious of their interaction together. And this can be around your powered network, particularly these days with this power distributed network, and it's a great little tool that we saw downstairs. I'm looking forward to having a play with that at some point in the future. But you can get these interactions where you get potentially little resonance points in your circuit because the capacitors are oscillating between each other. Now, there's nothing you can do about that, or not a lot you can do about that. In general, these peaks are not that high. Again, this is a measured plot. But what you can do, if you carry on using the same values, you can keep pushing this down and down and down. That's another reason to use the same values. It will push that whole curve further and further down. This is a single 1 microfarad and 1 nanofarad. And as a rule of thumb, I suggest a 100-to-1 ratio of capacitance values will keep that peak further apart. The closer you get those two capacitors together, actually the higher that resonance peak occurs. The further apart they are, the more it's spread out. And that's partly because it's not that 2 1 microfarad capacitors are not exactly 1 microfarad, and so that helps spread it out as well. The tolerance in the capacitance, the tolerance in the material, the tolerance in where you've placed it on your board. So all these things help spread it out. But if you push them too close together, so if you had a 1 microfarad and a 0.1 microfarad, potentially that peak can start to get quite high. And when you look at the analysis of what they do for these other capacitors, they only pull this bit down a bit further. So why worry about it? Why not just use lots of parallels of them and push the whole thing down? Here you're getting a very good rejection potentially between 10 kilohertz and 10 megahertz for just two capacitors. Imagine if that's 20 distributed over your board. That goes below the 0.1 ohm across the whole of the board for that big wide band of frequencies. Whereas if you start adding other little values in, and this is on the power network, If you have to have capacitors of all the values for frequency setting, etc., that doesn't matter. This is all where they're paralleled up on your power network. So with inductors, surface mount clearly shouldn't be as critical because they are wound, wired things. So the extra parasitic in an inductor from a lead is just more inductance, and it's at the picohenry sort of range, so it's not that critical. Here we have a thing called parasitic capacitance, as you might explain, affected by the winding style, which actually isn't often that quoted. When I did all these tests, I was working for a company that, as well as power supplies, we manufactured the windings for the power supplies and sold them as components as well. So I was quite fortunate that we were manufacturing windings as well. And so we got into the technology of having nicely wound things, or scramble wound, or layer wound, etc. We could do all this, and so we could see the effect of it. And also the form factor has an impact. What I mean by that is the type of core you've got in there. If it's a toroid, that's a closed core, or a bobbin, an eye-shaped cross-section, it's not a closed core, but nowadays you can get a bobbin with a shield on it, and that almost becomes a closed core again. So the form factor does have an impact, but it's not as critical actually as the winding style. But these are not easily obtained directly from the data sheet. But you can actually get the extra parameters you want from the data sheet because it is in there if you know where to look for it. So just like the capacitor, if you want to model an inductor, you can do that. And again, this is what you actually purchase, and they throw in these 3 extra values for next to nothing. You can get often the series resistance. That's usually quoted in the data sheet. It's a pretty straightforward number. You don't get this parallel resistance, but in this instance, that is not that relevant in general. You don't need it for settling of the component. And you can often get this winding capacitance, you can get the value at least, by the self-resonant frequency of the inductor if it's quoted in the data sheet. But you can even get this value if they have a quality factor quoted in the data sheet as well. Does anyone know what a quality factor means in inductor terms? It's a bit historic. It's from radio frequency days where you used to use an inductive element to tune a circuit into a radio frequency. And generally, the higher the quality factor, the peakier the inductor was. And actually, what you want for EMC is a really low quality factor. So you want what might seem counterintuitive to some extent, a low quality inductor, but that's because it's low quality for radio frequency. And if you're trying to not have radio frequencies in your circuit, that's exactly what you do want. So if you have this parameter, the self-resonant frequency, you know the inductance, you can actually calculate the winding capacitance from that equation. It's not a direct quoted number in the data sheet, but often self-resonant frequency is and the inductance is, so you can actually calculate that if you wish to model these more accurately. So as you might recognize, these look just like the capacitors, only upside down, as you would perhaps expect. They are inductive until they become capacitance, and it's the winding capacitance that has the effect. And you can see this quite easily, that the higher the value, the lower the value, the less windings there is on it, therefore the less capacitance there will be from the wire. Hence, it goes down. But ultimately, on the same core, it is limited. You can't get something on this core, even at a single turn, will not go much above, oh God, this is in that, it's not been analysed it, that's 100 megahertz. So you can actually get quite high frequency. Yeah, that's a gigahertz at the end. And if you have this quality factor, you can calculate that dissipative resistance value if you want to. It's, as I say, it's not that critical, but it will limit how peaky this is. But you can use that actually in itself to help you get rid of problems. I had a circuit with a switch mode power supply that just happened to have a resonance very close to a clock. I had an 8 megahertz clock, and it just so happened that the self-resonant frequency of my inductor was 7.9 megahertz. I hadn't realized this until I was getting some separation at about 20 times, so I had 160 megahertz peak, and then one very close to it, a little bit less. I realized it was the inductor. Now, it was at a stage where it was too expensive to change the inductor, too expensive to go to another manufacturer. So the solution actually was to get rid of its quality factor, it's quite a high quality factor inductor, by sticking a 10k ohm resistor in parallel with that inductor and squashing this quality factor down. And that was all it cost. So it cost pennies to fix the problem. just by knowing that it has this impact. So the higher that quality factor, the peakier this was, and it just happened it was resonating with a clock. So again, it was a very, very cheap way of solving that problem. So as I say, if once you know these equations of getting into some of these very simple components, you can get in there and you can solve and help yourself. I always nowadays, if I have an inductor, I leave a space for a surface mount resistor just in case, because once bitten, twice shy, as we say. There's a little impact here, actually. The arrow slipped, but this is a thing called skin effect. You ever come across skin effect? I always include this because it was the first time ever I've actually measured skin effect. I'd always read about it and knew its equation, but could never actually see it. But I physically actually measured it one day on this, so I've always left that in there just because it makes me happy. But as you can see, the core factor for similar inductors doesn't make that much difference on where these peaks are. It's more due to the winding style. So don't be trying to select an inductor. And I'm talking really here about power inductors, not about filters. For filters, you can probably use generally small. These are limited sometimes by size. So what will often change what you choose here is the physical size you have available on the board. Toroids for a certain current density are quite big, and so I have often used bobbin inductors in place of toroids to get the board space down. And if you still have a problem, there's not much. It's surprising actually. There's very little field emission from a bobbin inductor unless it saturates. So in normal operation, most bobbin inductors are actually pretty self-contained in their field. But if you're really worried about saturation, you can have shielded bobbins, which are virtually as good as a toroid, because their gap and where they saturate is just a very small gap between the edge of the bobbin and the shield. So even if it saturates, it doesn't leak a lot of field. They're very, very good. But just like we have this voltage effect with our capacitors, you also have a current effect with different types of form factors. Toroids are actually very good. When they saturate, they have a very slopey overcurrent. So you can actually, because the field is self-contained within the toroid itself when it saturates, you don't get much emission, but also you get a very gradual fall off. So this was a 1 amp toroid. So even at 4 amps, 4 times its rated current, it still had only fallen by 70%. It still was quite inductive and contained the field. Whereas with a rod inductor, it virtually collapses. That was a 4 amp rod inductor, and just over 4 amps, it collapses, and you get a massive field emission from it. So rods are definitely worth avoiding. With a bobbin, this was actually a 7 amp bobbin. By the way, the reason why these are different sizes is to try and illustrate that the density you can achieve from some of these materials. So this bobbin and this toroid were physically the same size, but you're getting 7 times more current density out of the toroid for that size. You take it the other way around, you can get a 1/7 of the board area for the same 1 amp result in a bobbin. So that's why I like bobbins. They're very dense, yet they do have a good fall off. It's a square law, actually. It will eventually saturate and collapse to 0, and then you'll get a big emission. But you can actually abuse them quite a lot without getting too much of a problem. So if you're looking for a middle ground. Now, again, when did EMC become a big thing? 1996, when the regulations came in. That's when EMC became, that's when I started making money. Just after that, when I wrote my book. A lot of the suppliers of these things, ferrite beads, started to make a lot of money because they were seen as a solution to lots of EMC problems. And in fairness, on certain lines, they're not bad. But this sort of level of rejection, a few dB. Another problem I have with beads is it's very difficult to sometimes work out what this means to your signal, particularly at DC. Generally in DC, it should go straight through, but there is a little bit of rejection. But these are quite expensive components for the amount of rejection they give you. My recommendation to you is go back and look at those resistors. If you want to get rid of high frequencies, a cheap resistor can give you very high impedance at high frequencies, and is a lot less expensive than a chip bead. But they work, they have their place. But this one still has fallen off at a gigahertz, whereas the resistors were still being inductive and still going up even at a gigahertz and beyond. So you might find that actually you get a better rejection from a resistor than you get from a bead sometimes, for a lot less money. And if you really want a big bead, these are things. These are the same as beads. People don't often appreciate that, but if you wanted to, I use this to test if occasionally if I really do need some beads on the line. If you put one of these around the line and it cures some of your problems, you probably need beads in the circuit. But that's all I use them for. I don't use them in general. But of course, they have their own application. They're probably on some of these lines here where you don't know what they're going to be connected to. So they're a sort of what we call belt and braces, just in case. So with discrete components, again, there's a little bit you can do here, but not quite as much as the passives. And part of the reason, of course, is passives are a lot cheaper. So if you say to your, if you have your own production, or you say to your CM, right, I only want to use a few passives, it's going to be these resistors, these capacitors, and that's it. They don't mind, that's quite nice for them. They can bulk up volumes, etc. But when you start chopping and changing discretes or integrated circuits, then it starts to have an impact on your BOM cost. But in general, there are some things you can do. So surface mount again. In general, use slower parts, but fast is often good for EMC with diodes because you can actually trap things which they're not there to trap if you use a fast diode. Depending on where you, but it does, the problem with diodes is it does really depend on the application. So I wouldn't use fast diodes, for example, in rectification, but if you're using them in other areas of still rectification but not of a power, then they're quite good to have a fast diode because it can get rid of ESD as well. Whereas transistors, it's the opposite of the above. And the way often I find that transistors are misused. So you use one which is actually much faster than you need, and I've been caught out myself, is because you've got a very simple circuit. Let's say it's just a flashing LED. As you might guess, I'm using this from my own experience. And so you've got a BOM already, and you've got a transistor there. That'll do. I'm only flashing LED, resistor, LED, transistor, flash, flash, flash. Just so happens that the gate voltage of that transistor was 650 megahertz. My LED is right on the outside line because it's showing me that something's happening. And of course, it's sending out 650 megahertz pulses into my LED. So I'm getting it. And you can do that quite simply by, as I say, in my case, by accident, just by using a transistor, because it was elsewhere in the BOM and I didn't want to go through the design of working out what's the best transistor to flash a bloody LED. I mean, God, it's an LED, it's a light. But there you go. Another reason sometimes that when Lee was talking about the evolution of parts and we're all going down to a single devices these days, that's actually helped with EMC as well, because often these days, the worst parts of EMC, particularly if you have an onboard memory, doesn't get out into your circuit board. And that's really good for EMC. It's bad for the power network, but it's good for EMC. And you can see it actually even in simple components like transistors, where things like, as you go to surface mount from a leaded part, all the parasitics reduce. So the bond wire parasitics is halved, the interlead capacitance is halved. And this is true on integrated circuits as well, I'll show you in a bit. So this move to surface mount and for more integration has actually helped with EMC as well. So it is a good effect. Now this is where, as I say, I've used these. In the case of again, rather than add another transistor to my BOM list, I persevered with the one I had, which caused me a slight problem. I actually passed EMC, but I didn't like the results. You can do things quite simply to your circuit to help you meet EMC performance without a great deal of cost. And basically, you just have to follow certain very simple design rules to improve the performance. So if you've got a gate or a base of a transistor, so I can remember, I have a pen that you can see. Oh, there we go. So we're back to analog circuits, which is the question I raised with Lee earlier. And these are already in there. So you want to use it. All you're doing is flashing a light or making some signal. It's very simple to just add a very small value capacitor here. In fact, with FETs, you often don't need the capacitor because the capacitor is already there. All you need to do is have a reasonable value of this so that the inrush can't be high enough to cause it to operate at full speed. If you're only flashing lights, particularly on I/O signals, very simple things like this, either flashing lights or sending a signal out to say something's turned on or something's turned off. Maybe you need quite a lot of current. Some of these are actually quite high current drivers, but you don't need them that speed. But unfortunately, you just happen to choose a component which, because of another function, is quite high speed. Sticking that, and it's quite easy to choose a value to limit this. In the case of FETs, if your voltage is whatever it is, VCC, you multiply that, I think, roughly by 100, and you'll get the value. So in other words, if it's a 5-volt rail, 470 ohms typically is enough to cause that to be too slow to react at full speed. Here it's VCC times 1K. So again, if it's 5 volts, that would be 4.7K. And that's good enough in the first instance to get you to really slow down these. You still need a capacitor in that case, but to really slow down those circuits at the cost of either a capacitor or a slightly higher value resistor. So it should be free because you should already have them in the circuit. You shouldn't be driving them direct from a gate. So it should be quite easy to do that and therefore avoid some EMC problems for no cost. All right, better go quick. One of the problems with capacitor, if you have it on the input, is that they actually can act as they can demodulate RF as well, so be very careful going the other way. You definitely might need capacitors going the other way as well. I have to go quick. So fast diodes. The reason why I might have a fast diode is, faster it is, the more it can cut off from things like ESD transients. But things to look out for is very low transit time. So if you're looking at a data sheet, you want low transit time, you want low reverse recovery, because they'll give you less ringing in your circuit. Integrated circuits. We've already mentioned a lot of this, so we'll go. In general, people overuse high-speed components, particularly digital. Lee talked about Sun before, and I worked with Sun actually, and a guy designed a 16 megahertz, 16-bit micro to run a washing machine. Now, no one needs the spin cycle accurate to a microsecond. That's ridiculous. An 8-bit PIC would have done what they wanted. So use something that's appropriate. But if you've got a software guy who's only used to using ARM, you will only ever have ARM processors in whatever design you've got. So look, you can actually find a lot of things like bandwidth limited parts and slew rate limited parts. They're a little bit more expensive, but they might save you a lot of cost in engineering parts like that into the output of your circuit. They already exist within that circuit. So if you can use them, do it. Again, this will be in your data. So you can see that basically going from through hole to surface mount to even denser surface mount and even further on to modern packages, lead frame, it really reduces the parasitics associated. And this is some of the reason why these packages are popular. It's not necessarily for the EMC performance. It's because you can get the power into them. And nowadays, getting all that power into these packages is more critical than the EMC performance, and you only can do it with very low parasitics. If you go to chip scale packaging or wafer scale packaging, it's even better. I think actually Moore's law, if Moore's law does continue, it'll be at this level at wafer scale packaging. You won't see it necessarily outside of the package. The problem with these, and it's not a problem I've come across, but some people will come across as you get higher and higher frequencies, is that as you get denser and denser packages, although it's easier to get the power in and out and the signals in and out, they more cross-couple because they're closer to each other. So you might have crosstalk issues. Nothing you can do about it, just be aware of it. It's there. If you go from a quad flat pack to a ball grid array, you might suddenly get crosstalk issues that you never saw before. Just be aware. And it's not your PCB, it's the package. But they won't guarantee it. Configurations, if you can use centralized power, it just makes decoupling easier. These days, this is more common anyway. Not many people use combinational logic these days, but one thing I try and identify, if you can, just use the same combinational logic. These days, this has all been replaced by PICs and micros that mop it all up, so it's not quite critical. It's one of the few areas, though, where immunity, which is very rarely discussed or identified in a IC, is actually easily identifiable here. Noise margin is a very good measure of immunity, and it's one of the few areas where if you can see that data on a data sheet, it gives you an indication of the immunity. The higher the noise margin, the higher the immunity of that part. And watch out for this effect, loaded drivers. You get more and more load you put on, the more and more current you start to pull through at high frequencies. And it's not always obvious when you're doing some of your tests at low frequencies, but when you start to fully drive circuits, particularly when, as we were demonstrated with as you start to plug in more and more boards, suddenly your current demand and your high frequency performance can become worse and worse as you plug in more. Fine when you did your test on your single board with nothing plugged into it. As soon as it gets more loads on it, it starts having either supply problems or EMC problems, or both. In fact, to some extent, this pseudo-ECL and PCIe and the coupled differential approach can be better above sort of 70 megahertz. Sometimes these, what are considered more generally power hungry, can actually be less power hungry at higher frequencies. So just be aware of that. You might, as you go past the 100 megahertz barrier, want to use a completely different communication technology on your backplanes. Now, one thing I will say on decouple every IC. Not only that, but where possible, decouple every power pin pair. So you can see, and again, using this 100 to 1, this is actually can be lower cost than a big bypass capacitor. Anyone use spread spectrum clocks? Not very good for communication, but it does reduce the overall power level you see at any one frequency. The problem is it spreads it out, and if you've got communication systems, your eye diagrams start to wobble around. But also, if you've got a test which requires peak hold, all it does is actually push that right the way across at the same level. So be very aware of your test methodology that's going to be used if you want to use spread spectrum techniques. It can look good initially, but if you've got a peak hold method of test, maybe specified by who's here in the automotive field, that's where it's going to catch you out. That's where it's caught me out. Let's be honest. These are things that I've had problems with. The trend for low operating actually is very good for EMC. It's actually been really good for EMC. I did a test with a PIC again, which could run at 3.3 and 5 volts, and in general, its emissions were down by 3.6 volts simply by switching its power supply to 3.3 from 5. So this general trend has actually been good for EMC. So it's not good for immunity in general, but then immunity tends to be in a peripheral interface where that's handled by analog-y type circuits such as interface chips. But buyer beware. I think we've, again, a lot of people, not only do PCB suppliers sometimes change what they do, your IC suppliers, they're trying to get more and more chips on the same die, so on the same wafer. So they die shrinking and they might not tell you. And the problem with die is the thing you're really interested in is the fastest rate of rise or the fastest rate of fall, and it's not a data sheet, it's the minimum rate that they give you in the data sheet. So they can change their process and make chips faster and faster and faster without having to change their spec. But that could eventually start giving you higher and higher frequency edges in your circuit, which you've not designed to cope with, and they've not told you about it. I think I'm running out of time, so I'll just skip through these. Mains components, generally not that problem. As I was trying to get early to, square waves are not square waves. Even then they're square, they've still got an edge rate, they've still got a finite rise time. And sometimes it's not just the frequency, it's the pulse width that has an impact. And you can calculate some of the effects you'll have if you know the pulse width, the rise time, etc. You can work out an envelope, and just to prove that if you're buying power supplies off the shelf and you know those effects, it does actually quite well match. Theory actually matches practice. So that's a measured DC-DC converter noise compared to its simulated ideal emissions from that graph. So you can't tell exactly where these peaks are going to be. You can see the envelope's pretty good. So you can use some really basic maths like that to estimate what you're going to get out of if you're buying packaged DC-DC converters. Just about it. Oh, how about that? 45 slides, that is. So it's always going to be secondary to functional performance. So, forget the fact that, Martin said this is a better component. If someone says I'm using an ARM7 and it's going to be 66 megahertz, even if I am driving a washing machine, that's probably what you're going to have to do. And you're just going to have to handle it. Where you can, though, surface mount preference. Generally, slower is better. And use these where other criteria are exhausted. So these should never necessarily be the primary reason you select a component. These are when you've got two sets of resistors, two sets of capacitors. If you can find one that's got a slightly lower series inductance and slightly lower series resistance, go for that one. you have any questions, I'm around all week. Well, I'm only around till tomorrow, but you can also find some in this book as well. It's a great book. Yes?
What would you recommend as a material if you have to deal with frequencies above 40 megacycles?
What, as a ceramic, as a capacitance material? I'd still use the ceramics. I mean, you can get high K mica capacitors. They are better and they work up to high frequency, but they're quite expensive, but you can get them. I would just use lots and lots of the lower values so that that curve just comes down at the higher frequencies. I'm afraid I'm very cheap when it comes to circuits because most of the stuff I've designed have to be for automotive, which are really... I spent one day taking off capacitors, seeing how far we could go before they failed the EMC test. So, you know, that's how cheap automotive companies are. But that's what I would do. I would throw in lots and lots of low-value, cheap capacitors to try and pull it down, rather than go for mica or the more expensive ones. But you can get the mica. If you've not got the space or you can't, you have to get to market a lot quicker, then go for the mica. It's very good.
Really impressed is also type 1 ceramics.
Yeah.
So if you use C0G, for example.
Yeah. To be honest, on a frequency scale, they're all the same. It's only the temperature and the voltage performance which actually differs between them. As far as the frequency performance is concerned, all ceramic material of that type is the same. Yeah, which has surprised me as well. But I was surprised how close they were. In fact, if you go back, the Wi-Fi V is slightly higher. It's 46 megahertz compared to 40 for the COG. So actually, in theory, on the frequency scale, Wi-Fi V is slightly better, very slightly. Yes. Oh, sorry. I've got a microphone here. I forgot about this.
Yeah, thanks. My engineers, they put for FPGA with very much of power pins, one capacitor for each pin.
Yeah.
So it's about 10 or 20 for the same voltage, but still they use power planes between it. Is it necessary to put so much capacitors, the same size and same value, one per each pin?
FPGAs are a real pain, and it probably is actually for FPGAs. If it was a microprocessor, what I do with microprocessors, I actually alternate between pairs between the low value and the high value. So if I'm doing 100 to 1, I'll have 1 nanofarad on one pair, and then 100 nanofarads on the next pair, then 1 nanofarad, then 100 nanofarads. But for FPGAs, I perhaps wouldn't do that. I might use a lot more, to be honest. But that's what I've done in the past for DSPs and microprocessors. But FPGAs are very, very difficult to predict the performance of, to be honest. Microprocessors are much more fixed architecture. Obviously, FPGA is field programmable, so the architecture that's going to happen is more difficult to predict, unfortunately.
Well, the main thing...
Yeah, still.
The main thing, what I meant was the difference. I use a power plane for power ground system, and so they are still all connected at some layers, and but they still use 20 or something of that capacitors next to each pin. So each pin sees 20 caps,
Yeah.
but I think sometimes it could be less than that.
Yeah, I apologise. I did, yeah. The power plane helps, but it isn't in itself as good as the capacitors that are right next to the pins. The power plane helps distribute the capacitance across the board, and it definitely helps quieten down the board near where your FPGA is. But what you don't want is the supply for that FPGA being drawn from the capacitor at another chip. And bulk capacitance and board capacitance is really poor. Some people say, oh, you can get a lot of capacitance out of your circuit board. You can't. Not only can you not get it out, but because of the frequency response of the dielectric in FR4 in particular, the actual effective area you get is determined by what's called the electrical length, which is just the rising edge. You can calculate it in an equation, the rising edge of the fastest pulse. So it's a very, very small area of capacitance in the board. So you get like femtofarads from the board itself. So the board, the planes are good, but they're not giving you any extra capacitance. But they are better, don't get me wrong. I would always promote using power planes and ground planes, but not to give you capacitance. So if you, and sorry, but FPGAs are the worst for anything like that. So yeah, I'd still use a lot of capacitors, I'm afraid, on FPGA. Sorry. I like to be cheap, but in your case, I'm afraid I can't.
One question from automotive side. What about bulk current injection immunity? What can you say about it? If there are any precautions that we can take in order to avoid that, to pass the tests, you know?
Yeah, bulk current injection is the worst test there is, isn't it? For those who aren't aware of the automotive test, you put a cable clamp, a bit like one of those ferrite beads, and then you inject a current into it, and so you inject a current into your whole cable bunch and push it up for testing immunity, and you can do the reverse for emissions. The only thing you can really do in that is some of those resistors. You get those low power resistors, but the problem is it's only up to about 20 megahertz, isn't it? So it's not, even some of them aren't going to be doing you much good.
Because I'm wondering if there is a method to find out which is the component that will absorb the power.
Yeah. Yeah, it's very tricky to be honest, because it will vary from circuit to circuit. I've used resistors on some tracks which are not current dependent, so very low. I've used small value 50 ohm resistors, but mostly I've actually been able to do it in automotive with actually capacitors which I've been primarily using actually for ESD. So a 1 nanofarad capacitor on every input pin, which primarily is there for ESD, but it slows down that bulk current injection rate of rise. So it doesn't stop it entirely, but it slows it down enough to be able to handle it by other circuits, by things like a clipping diode within an IC. Because all ICs in their bond pad structures have a diode, a clipping diode on their inputs. And if you can get rid of the peak energy on a BCI, often that plus any resistance or impedance in the lead, plus the clipping diode in the bond pad. So this isn't actually part of the structure. You'll see it in the IBIS model. If you get the IBIS model, the clip-in diode can be enough actually to cure a lot of BCI. I won't say most, but a lot of them. My main problem actually with BCI has been different harness lengths, rather than, so you design a circuit to pass the CISPA 25 test, which is a 2-meter harness. They go and stick it on a vehicle, put a bulk current injection on it. It's a 14-kilometer harness, and you get a completely different result. So I'm afraid my personal problems with BCI have been due to harness differences rather than component problems. But I have had lots of problems, but that's been the main source of that. Yeah.
I have another question concerning resistors.
Yeah.
So if you have high-value resistors, let's say about 47K, 100K and above, for example, for putting a voltage to a varactor diode,
Yeah.
for controlling a frequency, how does the impedance behave at higher frequency? Does it rise also, or with these high-value resistors, do they become more capacitive at higher frequencies?
Providing it's a surface mount and it's not a metal film, it continues with a very, it rises up. It does become inductive, but at high loss. So it's actually very good. They're actually very good. If you have a metal wound inductor, they actually, at very high frequencies, it overcomes the inductance and they become capacitance due to the wire, and they fall off very rapidly. But within that, they actually have a very severe resonance peak, depending on how they wound. If anybody, just a quick tip, if anyone actually does go for wire wound, see if you can get a thing called reverse helical winding. What they do is they wind it one way, and then in the middle they stop and wind it the opposite way, and so it cancels itself. So if you ever do have to use a wire wound resistor, go for something called reverse helical winding. Again, it's not a very generically well-known topic. I just happen to be a bit sad, really.
All right, guys, so I want to thank Martin, because we just went over a little bit over, so we just have to cut off. Obviously, he's going to be around. We can ask him questions while he's here. So thanks again, Martin.
Thank you.